Hey class, let's pick up on the binomial distribution section. We did the first four problems, which was really just vocabulary pertaining to Bernoulli trials. Starting with number 5, excuse me, starting with number 5, we're going to look at doing some calculations of these binomial probabilities. Number 5, yours will be very similar. I just wanted to show you how to work on these on the statistical analysis software that comes with your WebAssign. Richard has just been given a 4-question multiple choice quiz in his history class. Each question has 5 answers, of which only one is correct. Since Richard has not attended class recently, he doesn't know any of the answers. Assuming that Richard guesses on all 4 questions, find the indicated probabilities. Round your answers to 3 decimal places. Okay, so each question is independent of one another. There's 4 questions, so what we'll do is we'll have n equals 4. I'm just jotting these down on my notebook so I don't lose them. So there's 4 questions, each independent of one another. There are 5 possible answers, only one is correct. So P is 1/5 or 0.20. Assuming Richard guesses on all 4 questions, we're going to find the indicated probabilities. Okay, so part A, what is the probability that he will answer all questions correctly? So for A, we're looking for the probability of 4, P of 4. When I open up SALT, in the top left, we're going to switch from normal distribution to binomial distribution. Number of trials. There are 4 questions on the test. The probability of getting one right, and you can click, you don't have to use the up or down, you can just override the number, is 0.20 for 1 out of 5. Okay, now I'm going to go over here to the top right and select equal, and that changes my probability option here. The probability that all 4 are guessed correctly is 0.0016. Okay, so I'm going to go back. Excuse me. There we go. 0. And let's see, we've got to round to 3 decimal places, so 0.002. What is the probability that he will answer all questions incorrectly? That means he will get none of them right. So probability of 0, and these are exact again, so that's 0.4096. So probability of 0. Notice it highlights the bar that you're on, like that first bar is pertaining to 0, and it gives you if you were to smash all these bars together, it'd be a histogram of these probabilities. So we've got, now again, rounded to 3 decimal places. The 6 is going to make the 9 a 10, so 0.410. Whoops. 0.410. What is the probability that he will answer at least one of the questions correctly? At least one. What does that tell us? At least one would be 1 or more. 1 or more. one or more would be right-tailed. So that would be, we still have 4 questions, 1 out of 5 chance of getting it right. I switched to right-tail because that's more. At least one. That carries a 0.590 probability. I'm not exactly sure about this table that's given. These answers should be equal. They could be off a little bit due to rounding error. And then finally, what's the probability that Richard will at least answer at least half the questions correctly? That's 2 or more. So we're going to change that to 2 for 2 or more. At least 2. That carries a probability of 0.181. 0.181. Okay. I'm not 100% on this top one. I'm going to go ahead and submit. Okay. So they're all good. Whether you use a table or the SALT analysis package, those come out. Okay, I'm going to go ahead and move up to number 6. Before 1918, approximately 60% of the wolves in a region were male and 40% were female. However, cattle ranchers in this area have made a determined effort to exterminate wolves. From 1918 to the present, approximately 65% of wolves in the region are male, 35% are female. Biologists suspect that male wolves are more likely than females to return to an area where the population has been greatly reduced. Before 1918, a random sample of 10 wolves, so N equals 10, were spotted in the region. What is the probability that 7 or more were male? P is going to be 0.60 because that's the before 1918 statistic of males. So N is 10, P is 0.60, and we're going to be looking for R being greater than or equal to 7. So let's go back to our analysis package. We're going to change N to 10 for 10 wolves. The success of, which is considered to be a male in this problem, doesn't mean good or bad, 0.60. And we want to be values of 7 or greater. So we're still going to leave it on right tail, but we're going to move this probability up to 7. Notice those bars keep climbing. 7 or more, that's the orange bars, totaled 0.3823. I've actually got to go back and see what our rounding expectation is. 3 decimal places in this one. Okay. So 0.382. 0.382. What's the probability that 7 or more were female? Female, all we have to do is change our probability to 0.40. Again, you can either directly edit or you can use those up or down arrows. 0.055. The 7 makes the 4 go up. 0.055. What is the probability that fewer than 4 were female? Fewer than 4. Female, we don't change our probability. Fewer means we need to go left tail. And if it's fewer than 4, I would assume that's 0 to 3. 0 to 3. And that carries a probability. Noticing that those bar graphs that are orange, if you were to smash all these together, you'd have a histogram, but only the ones highlighted in orange are 3 or lower. So that's fewer than 4. 0.382. Okay, so part B is for the updated part. So we're going to use the second set of statistics. For the period from 1918 to the present, in a random sample of 10 wolves spotted in the region, what's the probability that 7 or more are male? Okay, for the updated stats, the males are 0.65, the females are 0.35. So when we go to salt, we're going to have to change. And now our sample size is still the same. We still want 10 wolves. But now the probability of selecting a male, 7 or more are male. We've got to change this to 0.65. Or more tells us right tail. 7 or more. That's 0.514. Seven or more, 0.514. What's the probability that 7 or more were female? Change our probability to 0.35. 10 wolves, 35% female, 7 or more, that's 0.026. 0.026. And then finally, the probability that fewer than 4 were female. Fewer than 4 would be 0 to 3. Female, we don't change our probability. We do make it left tail. You have to pick up on those verbal cues. Less than or equal to 3. That's 0.514. Rounded to 3 decimal places. 0.514. And keep your fingers crossed. And they're all correct. Number 7, the figures below show histograms of several binomial distributions with n equals 6 trials. Match the given probability of success with the best graph. Whatever your probability is, that's where you're going to expect your high point. So 0.30, you would expect highs in the low end of the graph, right skewed. When the probability is 50-50, you expect the highest bar to be right dead in the middle. So that's 1. 0.65, you expect your bar to be the highest about 65% of the way. And 0.90, you would expect your highest bar at the 90% area. In general, when the probability of success is P is close to 0.5, and that was that upper left graph, you expect a symmetrical graph. When the probability of success is close to 1, then you would have bars highest on the far right end, which makes it left skewed left. The long slopey part is the skew, so left skewed if all your bars are high on the right. Skewed left when the probability is close to 1. If it's close to 0, all your tall bars are on the left, and then they would slowly skew off to the right. All right. And then this is our final one. We have, let's see. In Hawaii, January is a favorite month for surfing since 60% of the days have a surf of at least 6 feet. You work day shifts in a Honolulu hospital emergency room. At the beginning of each month, you select your days off, and you pick 6 days at random in January to go surfing. Let R be the number of days the surf is at least 6 feet. I'm just getting a clean sheet of paper, y'all. Sorry about all the paper rustling. Okay, so we're going to make a histogram. All right, so N is 6. P is 0.60. And let R be the number of days the surf is at least 6 feet. All right. So what we'll do is we'll go in here. We're going to leave it on binomial because either the surf's 6 feet or more or not. That probability is 0.60. And I'm going to switch this to equal. Okay, so let's pretend that we smash all these bars together and see if we can't come up with the right bar graph. This one looks pretty close. This one does too. So we're going to need to do a few probabilities. Let's see. If we do probabilities for 3 and 4, that should help us distinguish if this is the correct graph. Okay. So when it's exactly 3, we have 0.276. When it's 4, we have 0.31. Okay. This is the only bar graph, histogram, where 4 is 0.31 and 3 was might as well call it 0.28. So I'm going to go with this one. You can check it for all 7 of these bar heights. All you have to do is progressively change. Notice on the right side of your screen, when I drop or raise these probabilities, different bars are highlighted. The height of them is the probability. So this is a probability histogram. 0. But you get the general idea. 3, 4 is taller. If we go up to 5, that's way shorter. So I'm comfortable picking this upper right histogram. What is the probability of getting 4 or more days? Or more says right tail. And I'm going to change this to 4. 4 or more is 0.544. What is the probability of getting fewer than 2 days? So that would be none or 1. Fewer tells me to go left tail. Fewer than 2, let me make sure that's the wording. Yep, fewer than 2 would be 1 or less. That's 0.041. Okay, now D, what is the expected number of days when the surf will be at least 6 feet? This is the average. Mu is equal to NP. So you will multiply 6 times 0.60 to get 3.6 days. NP is the expected or average number of days. Standard deviation, that is NPQ. All right, so if P is 0.60, that's success, then 0.40 has to be failure. And so we're going to take 6 let's see, and we've got a square root. So sigma is equal to square root of NPQ. That is square root of 6 times 0.60 times 0.40 square root 6 times 0.60 times 0.40. I get 1.2. 1.2. I was going to see if it had a direct path on here. But anyway, the average, or mu, is n times p. The standard deviation is square root of n times p times q. P and q have to add up to 1. And then finally, part F, can you be fairly confident that the surf will be at least 6 feet high on one of your days off? Yes, because the probability of at least one day with a surf of at least 6, so at least 1, would be what, 2 or more? Or 1 or more? Yeah, it'd be 1 or more. 0.996. That's a very high probability. And the expected number of days when the surf will be at least 6 feet is greater than 1, because our expected was 3.6, so greater than 1. All right, I'm going to submit. Let's keep our fingers crossed. Okay, so I felt confident about that histogram. And SALT makes it very easy to put these probabilities in. You just have to be careful with your verbal cues. N is the number of trials. P is the probability of success. And then Q will be whatever makes that go to 100. So if 60% success, then there's 40% failure. And anyway, I hope this helps. Please contact